Hello, our lesson today is about conics. First, the name conics. Where is it from? Let's see. So, the word conics from cone, and in fact, the four conics that we know, which are circle, ellipse, parabola, hyperbola, are the intersection between a plane and a cone or two cones. Let's see how. So here in this applet, we have, as you can see, two cones, vertically opposite, and a plane. This plane is intersecting one of the cones. Now, if we change the angle of this plane with respect to the base, okay, let's see here. So if I change this angle, you notice here that the intersection at this exact angle between the plane and the cone is a circle, right? So it's a circle, it's one conic. Now if the angle is changes in this way, of course you notice that the shape in this case is not a circle anymore, it's an ellipse. So it is the second conic. Now if I continue changing this angle, okay, at one point when the plane becomes parallel to the extremity of the cone, we will have a parabola. This shape, which is the intersection between the plane and the cone, is a parabola. And of course, if I continue also, in this case I will have two intersections, one intersection with the first cone and another with the second cone. This shape is the hyperbola. So in this, like this, by this method, I can find the four conics, which are circle, ellipse, parabola, and hyperbola. Now, why do we study conics? Conics in real life. Where do we find conics? In fact, conics are found everywhere around us. For example, the light beam is a conic. It's in fact a paraboloid. If we throw an object from the earth, the trajectory of this object will be a parabola also. The planet's orbit around the sun is an ellipse shape, and many others. Let's see, for example, here in this figure, the light beam, the Eiffel Tower, for example, the base of it is built as a parabola. The planet's orbits are ellipse. The American football is shaped also in this way as an ellipse because it rotates quicker and moves quicker. Here, for example, in industries, the large cooling towers are hyperbolic shape. The guitar also is in a hyperbolic shape, which gives it this unique sound. Now, an important thing also about conics. Each conic has two fixed elements, point and a line. In fact, the ellipse, for example, it has two fixed points that are called foci, focus 1 and focus 2, and one fixed straight line, which is a directrix. Here is a way to find the focus and the directrix of each conic. Now let's see if we have like this, like in this image, a cone, okay, and imagine the plane, the yellow plane. In this case, it's intersecting the cone at a shape. It's clearly an ellipse. Imagine that we can put in the two parts because it's obviously this plane is cutting the cone into two parts. In the first part, we put a sphere that fits exactly in it. Also in the second part, a larger sphere, also fitting exactly. So this sphere touches the surface of the cone from inside, okay? And also it will touch the plane. Now, the intersection between the two spheres and the plane are 2 points. These points are the foci of this conic, which is an ellipse. And the intersection between the spheres and the cone from inside, as you can notice, it will form like a circle, right? Now this circle, if I extend this circle, right, like this, for example, I will get a straight line on the plane, okay? You can imagine that. So this straight line also is the directrix. Each straight line is a directrix of the conic. So in this case, in that way, you can find the directrix and the focus of each conic. Now, by definition, what is a conic? Okay, summing this up, so a conic, if we have a straight line D and a point F that doesn't belong to D, suppose we have a real number E, positive number, a conic of focus F, directrix D, and eccentricity E. These are the three elements of a conic, F, D, and E. And we can denote the conic by C, F, D, E, is the set of points M. So it's the set of all points M such that the ratio MF over MH equal E, knowing that H is the orthogonal projection of M on D. So MH will be the distance between the point M and the directrix D. MF is the distance between the point M and the focus. The ratio between these two distances, MF over MH, is equal to E, the eccentricity. In this case, we have a conic of focus F, of directrix D, and eccentricity E. So that's the definition of a conic, any conic. Now, the four conics differ in eccentricity, mainly. Okay, so the eccentricity of a parabola is 1. If the eccentricity is less than 1, then the conic in this case is an ellipse. If it's greater than 1, the conic is a hyperbola. In case of a circle, the eccentricity will be 0. Let us begin with the parabola. Another applet here, created by me. In this applet, you can see that a parabola has an eccentricity 1, indeed, because if we take any point, so here M is a point on the parabola, as you can see, the distance between M and H, as it is here, is 10.47 centimeter. The distance between M and F, which is the focus, also is 10.47. Of course, you notice that H is on the directrix, so the line where H is the directrix. Now, if I move M on this parabola, you notice that the distance will be exactly the same. Okay, so the distance between M and H and M and F are the same, which means that the ratio MF over MH is equal to 1, which means that the eccentricity is equal to 1 whenever M is on this parabola. Let's study this parabola. In order to study the parabola, we need to find the equation of it. Okay, first, let's remember what is an equation. An equation of anything, of a line, of a circle, of a conic. So the equation is the relation between the coordinates of a point. You know that any shape or conic or any curve is formed of points. The relation between the coordinates of any point on this curve is the equation. Okay, so the conic, here the parabola, is a set of points. The relation between the coordinates of any point is called the equation of the parabola. Here let's take a point M. This point M belongs to the parabola. This parabola, it has a focus F, as you can see in the figure. It has a directrix. The directrix also, this is the directrix. Let's say that the distance between the directrix and the focus is P. Okay, take P as the distance between directrix and focus. First, the coordinates of F, which is the focus. If IF is P, then of course the coordinates of F are P over 2, 0, because in this case you can understand, of course, that since it's a parabola, when M serve this conic, the parabola, and get to the point O, and at this point OF is equal to OI, of course, so O is the midpoint. That's why the coordinates of F are, in this case, P over 2, 0. Now the coordinates of H, the abscissa is minus P over 2, because it's the same abscissa as I, and the ordinate is the same ordinate as M, which is Y, because we took M as a variable point of coordinates X and Y. Now what do we know here about this parabola? We know that the eccentricity is equal to 1. If the eccentricity is equal to 1, then the ratio MF over MH is equal to 1. Now, if MF over MH is equal to 1, means that MF and MH are equal. So, if we square both sides, MF squared would be equal MH squared. And you know that MF squared is equal to the distance, MF power 2, which is x of f minus x of m power 2 plus y of f minus y of m power 2. Same idea for mh squared. Here, using the coordinates, we will get that p over 2 minus x all to the power 2 plus y power 2 is equal to minus p over 2 minus x all to the power 2. Now, after a simple calculation and simplification, we will get the equation of the parabola, which is y power 2 equal to px. It's the general equation of a parabola.